All right, let's dive in. We're going to pull back the curtain on one of the most fundamental forces in the entire universe. And stick with me, because by the end of this, you're going to have the exact toolkit you need to calculate it all on your own. So let's get right to it. Okay, so have you ever felt that little zap of static electricity? You know, when you touch a doorknob on a really dry day, or maybe when you pull off a wool hat and your hair just goes crazy? It feels totally random, right? Well, I'm here to tell you it's not. That little spark, that strange pull, that's actually a tiny little peek at this incredible invisible force that's running the show all around us. And today, we're not just going to talk about it, we're going to give it a name, and even better, a formula. All right, let's start with the basics of this invisible push and pull. What is actually going on, way down at the microscopic level that creates that spark?
It really all boils down to one simple idea. You've got these tiny particles everywhere, and they have a special property called electric charge. And this charge comes in just two flavors. You've got positive and you've got negative.
And these charges, they live by one very simple rule. If the charges are the same, like two positives or two negatives, they push each other away, they repel. But what about opposite charges? Well, they do the exact opposite. They attract, they pull towards each other. And here you can see that idea in action, right? You have a positive charge and a negative charge, and they feel this force, this constant pull drawing them closer. It's a really simple idea, but trust me, it is the foundation for absolutely everything we're going to get into. Okay, so we know these forces exist. We know there's a push and a pull, but how strong are they? How do you actually measure that? Well, a French physicist figured it out, and he gave us something called Coulomb's law. Yeah, way back in the 1780s, this physicist, Charles-Augustin de Coulomb, did all these super careful experiments. And what he came up with was a law, a rule, that could perfectly calculate that force, that push or pull between any two charges. So what he found at its heart is pretty simple. The more charge you have, the more force you get. Makes sense. But here's the really crucial bit. The farther apart they get, the force gets way weaker. And not just a little weaker. If you double the distance, the force isn't just cut in half, no. It drops all the way down to 1/4 of what it was. It weakens super, super fast. And this is it. This is the famous equation that wraps it all up. I know. It might look a little intimidating with all the letters and symbols, but once you know what each piece does, I promise, it becomes your best friend for tackling these kinds of problems. So let's just break it down real quick. F, that's the force. That's what we're trying to find. The Q1 and Q2, that's just how much charge is on each of our two particles. Simple enough? R is the distance between them. And K? Well, K is just a special number we call Coulomb's constant. And this constant, this K, it is huge. We're talking 9 billion. That gigantic number tells us something really important. This electrostatic force is, by its very nature, incredibly powerful. At the scale of atoms and molecules, it completely blows gravity out of the water. All right, so the theory is cool and all, but let's get practical. Let's actually use this stuff. I'm about to give you a super simple 3-step game plan that you can use to solve pretty much any basic Coulomb's law problem. Seriously, it's this easy. Step 1, figure out what you know. List out your charges and the distance. Step 2, always write down the formula first. And step 3, just plug in your numbers and solve for the force. If you do it in this order every single time, you'll avoid all those little common mistakes. So for that first step, you just look at the problem you're given, and you'd pull out the numbers. What's the value of the first charge? Q1. What's the second one? Q2. And how far apart are they? What's R? Just jot them down on the side, so you have everything ready to go. Now here's a really important tip. The formula itself tells you the strength of the force, how big it is. But what about the direction? Is it a push or a pull? For that, all you have to do is look at the signs of the charges. If they're opposites, it's attraction. If they're the same, it's repulsion. That's all there is to it. Okay, let's take a big step back for a second. Why are we even talking about a law from the 1700s? Well, because this invisible force, it's not some dusty old piece of history. It is literally the glue that holds our entire world together. So if you remember anything, remember this. The force gets stronger with more charge, and it gets weaker really fast with more distance. And that one beautiful rule explains everything from why your socks stick together in the dryer, all the way up to the chemical bonds that hold molecules together. I mean, just think about it for a sec. Chemical bonds? That's just Coulomb's law in action, holding atoms together. Why do materials behave the way they do? It's all about the push and pull between charges. And the entire world of modern electronics, I'm talking about the processor in your phone, the screen you're looking at right now, it's all built on our ability to understand and control this one fundamental force. So yeah, this law is everywhere. It's inside the atoms of your body. It's powering the technology in your hands. It's at work all across the universe. It's this timeless, essential piece of the cosmic puzzle. And so, the real question isn't just about what it does. It's about what comes next. Now that you understand how it works, what are we going to build with it?